October 14, 1943. 30,000 feet above Schweinfurt, Germany. The sky erupts in flame and metal as flying fortress Memphis Belle II takes a direct hit from German flak. The B-17's No. 3 engine is on fire. Hydraulics are failing, and worst of all, the landing gear is jammed in the down position. Below them, 200 miles of Nazi-occupied territory stretch between the crew and safety. Above them, German fighters circle like vultures. Lieutenant Colonel James Hammer Harrison fights the controls as his bomber bleeds altitude. The extended landing gear creates so much drag that the plane can barely maintain flight. It's a death sentence. Bombers with stuck landing gear don't make it home. They crash in enemy territory or ditch in the English Channel. The 10-man crew knows it. They've seen it happen dozens of times before. But what Harrison doesn't know is that 500 miles away, in a cramped workshop at RAF Bassingbourn, a self-taught welder named Eddie Thompson is putting the finishing touches on a device so simple, so brilliant that it will soon save his life and the lives of nearly 2,000 other airmen. A device that the Army Air Corps had initially rejected as too dangerous and completely insane. This is the story they don't teach in history class. The story of how a stubborn welder from Detroit with no engineering degree and a reputation for being completely mad solved a problem that was killing hundreds of Allied bomber crews. Stay until the end, because what happened next shocked everyone, including the Germans who thought they had figured out how to bring down American bombers. But first, let's go back to where it all began. By the autumn of 1943, the Allied bombing campaign over Nazi Germany had reached a critical phase. Operation Point Blank, the systematic destruction of German industrial capacity, depended entirely on the massive Boeing B-17 Flying Fortress bombers that took off from English airfields every morning, carrying 10-man crews deep into the heart of the Reich. But there was a problem that was quietly bleeding the Allied air forces to death. Not German fighters, though they were deadly. Not anti-aircraft artillery, though it filled the sky with explosive steel. The problem was much more insidious, much more technical. It was the landing gear. When a B-17 Flying Fortress took battle damage, one of the most common malfunctions was hydraulic failure. When the hydraulics failed, the massive landing gear would often drop down and lock in the extended position. In aviation terms, this was catastrophic. The extended wheels and struts created enormous drag, like trying to drive a car with the emergency brake on. The bomber's speed would drop from 180 miles per hour to barely 120. The fuel consumption would double. Most critically, the aircraft became a sitting duck for German fighters. The statistics were horrifying. Between June and October 1943, 847 American bombers had been lost over Europe. Of those, intelligence estimates suggested that nearly 200 had gone down not because of direct enemy action, but because mechanical failures had made them vulnerable to attack. Landing gear malfunctions were the leading cause. Every day the problem persisted, more men died. Bomber crews began calling extended landing gear the Widowmaker. Some pilots, faced with stuck gear, would attempt desperate maneuvers to shake it loose, often tearing the aircraft apart in the process. Others would order their crews to bail out over enemy territory rather than attempt the nearly impossible flight home with the gear extended. The Army Air Corps had tried everything. They'd redesigned the hydraulic systems, added backup pumps, modified the gear doors, even installed explosive bolts to blow the gear off entirely. Nothing worked consistently. The explosive bolts were particularly problematic. They often damaged the aircraft's structure or failed to detonate at all. Engineers at Boeing, Wright-Patterson Air Force Base, and Bell Aircraft had spent thousands of hours trying to solve the problem. They'd produced sophisticated solutions involving backup hydraulics, mechanical overrides, and complex gear retraction systems. Every solution was either too heavy, too complicated, or too unreliable. Some required modifications that would take months to implement across the bomber fleet. Others worked in testing but failed under combat conditions. The most promising solutions required parts and materials that were desperately needed elsewhere in the war effort. Meanwhile, every week brought new losses. Experienced bomber crews, men who had survived dozens of missions over Germany, were dying because of a mechanical problem that seemed unsolvable. The psychological impact on other crews was devastating. They could face German fighters, they could endure anti-aircraft fire, but the thought that their own aircraft might betray them, that a simple hydraulic failure could doom them to certain death, was eating away at morale. Squadron commanders were reporting that some of their best pilots were becoming increasingly reluctant to fly. Ground crews were working around the clock, trying to prevent hydraulic failures, but the stress of combat operations made some degree of mechanical failure inevitable. The bomber offensive was in danger of grinding to a halt, not because of enemy action, but because of an engineering problem that nobody seemed able to solve. The situation was desperate. Every day the problem persisted. The Nazi war machine grew stronger. German industrial production was increasing despite the bombing campaign, partly because so many bombers were failing to reach their targets or were being shot down after mechanical failures left them vulnerable. Into this crisis stepped Eddie Thompson, a man who had no business being anywhere near military aviation. Thompson was a 34-year-old welder from Detroit, Michigan, who had never been inside an airplane before arriving in England. He had no college education, no engineering degree, no formal training in aeronautical design. What he had was 20 years of experience fixing things that other people said couldn't be fixed. Before the war, Thompson had worked at the Ford River Rouge plant, where he'd earned a reputation as the guy who could weld anything to anything. When other welders gave up on a job, when engineers said something was impossible, they called Eddie Thompson. He'd fixed blast furnaces, repaired locomotive engines, and once famously welded a cracked engine block back together while the factory was still running. Thompson had volunteered for military service immediately after Pearl Harbor, but the Army had taken one look at his age and his lack of formal education and assigned him to aircraft maintenance. He'd been shipped to England in early 1943 and assigned to the 91st Bomb Group at RAF Bassingbourn, where his job was supposedly to maintain and repair the sheet metal structures of damaged bombers. But Eddie Thompson was not a man who stayed within the boundaries of his job description. Within weeks of arriving at Bassingbourn, he was spending his off-duty time crawling through damaged bombers, studying how they were built, learning how they worked. He'd never seen anything like the B-17 Flying Fortress. It was a marvel of engineering, all aluminum and steel and complex systems, but to Thompson's experienced eye, it was also a machine, and machines could be understood, modified, improved. The landing gear problem particularly fascinated him. He'd seen bomber after bomber come limping home with their gear stuck down, watched as ground crews scrambled to find solutions that never seemed to work. He'd listened to the frustrated conversations between pilots and mechanics, heard the despair in their voices as they described friends who hadn't made it home because of mechanical failures. "There's got to be a way," Thompson would mutter to himself as he worked. "Every problem's got a solution. You just got to think about it different." His fellow mechanics thought he was obsessed. Sergeant Mike Kowalski, Thompson's bunkmate, would later recall, Eddie would lie awake at night staring at the ceiling, talking about gear mechanisms and hydraulic pressures. We thought he was going crazy. Here we are, getting bombed by the Luftwaffe every other night, and Eddie's worried about landing gear. Thompson's initial observations were dismissed by almost everyone. When he suggested that the Army Air Corps was approaching the problem wrong, that they were trying to fix the hydraulics when they should be thinking about the gear itself, his supervising officer told him to stick to welding and leave the engineering to the engineers. But Thompson couldn't let it go. He'd grown up during the Depression, when you fixed things because you couldn't afford to replace them. He'd learned that the best solutions were often the simplest ones, that complicated fixes usually just created new problems. He looked at the sophisticated solutions being proposed by trained engineers and saw overcomplication. Solutions that might work in a laboratory but would fail under the stress and chaos of combat. "They're thinking like engineers," Thompson explained to Kowalski one evening as they sat in their barracks. "All complicated and fancy. But this ain't a laboratory. This is war. You need something that works when everything else is going to hell." The breakthrough came on a rainy Tuesday morning in September 1943. Thompson was working on a B-17 that had returned from a mission over Bremen with its port landing gear partially extended. The hydraulics had failed, leaving the gear neither fully up nor fully down. It was exactly the kind of problem that usually meant the aircraft would be grounded for days, while mechanics tried to coax the gear back into position. Thompson crawled underneath the bomber, studying the landing gear mechanism. The B-17's main landing gear was a marvel of engineering complexity. Each gear unit weighed over 300 pounds and was held in the retracted position by hydraulic pressure and mechanical locks. When the hydraulics failed, the gear would often fall partway down due to gravity and air pressure, but the mechanical locks would prevent it from either retracting or extending fully. As Thompson lay on his back, looking up at the stuck mechanism, something clicked in his mind. The problem wasn't the hydraulics. The problem wasn't even the mechanical locks. The problem was that everyone was trying to fix the gear, when what they really needed was a way to get rid of it entirely. What if, Thompson said to himself, instead of trying to get the gear up, we just cut it off? It was a crazy idea. Landing gear was essential for well landing, but Thompson's practical mind immediately began working through the implications. If a bomber with stuck gear was probably going to crash anyway, what difference did it make if the gear was there or not? At least without the gear, the plane might make it home, where the crew could bail out over friendly territory or attempt a belly landing. He started sketching ideas in a notebook he always carried. The landing gear was attached to the aircraft by massive steel pins and bolts. If you could somehow cut through those attachment points quickly and cleanly, the entire gear assembly would simply fall away. The aircraft would be damaged, certainly, but it would be flyable. But how do you cut through steel bolts that are designed to hold 300-pound gear assemblies under the stress of landing? You'd need some kind of cutting charge, something that could sever the connections instantly and completely. Thompson had used cutting torches before, but a torch would take too long and couldn't be used safely inside an aircraft filled with fuel and oxygen. Then he remembered something from his days at the Ford plant. During the construction of new factory buildings, they'd used shape charges to cut through steel beams. The charges were small explosive devices that focused their energy in a narrow line, like a high-powered cutting torch, but instantaneous. The military used similar devices for demolition work. Thompson's idea began to take shape. What if you could mount small shape charges at the critical attachment points of the landing gear? Wire them to a simple electrical switch in the cockpit. When a pilot found himself with stuck gear over enemy territory, he could flip the switch. The charges would detonate, and the gear would fall away instantly. It was elegant in its simplicity. No complex mechanisms, no hydraulic systems, no moving parts that could fail. Just a small explosive charge and a switch. But as Thompson sketched out the concept, he realized the enormous technical challenges involved. First, where exactly would you place the charges? The landing gear had multiple attachment points, and all of them would need to be cut simultaneously. If even one attachment point remained, the gear would hang partially attached, creating even more drag and potentially damaging the aircraft structure. Second, how would you ensure the charges detonated at exactly the same time? If the charges fired sequentially, the gear might twist or bind, potentially damaging the wing or fuselage. Third, and most critically, how would you design charges that were powerful enough to cut through hardened steel bolts, but not so powerful that they would damage the aircraft's structure or injure the crew? Thompson had no formal training in explosives, but he understood physics and engineering principles. He spent his evenings in the machine shop, studying technical manuals, learning about shaped charges and explosive cutting techniques. He requisitioned small amounts of explosive materials, claiming he needed them for routine demolition work around the base. "You really think this could work?" Kowalski asked one evening, finding Thompson hunched over his sketches and calculations. "I know it could work," Thompson replied. "The question is whether I can build it safe enough that it won't kill the crew when they use it." Thompson knew that getting official approval for his idea would be impossible. The Army Air Corps had already invested enormous resources in sophisticated solutions developed by trained engineers. They weren't going to listen to a welder who wanted to strap explosives to their bombers. So he decided to build a prototype in secret. Working in the base machine shop during off-duty hours, Thompson began fabricating the components for his gear jettisoning system. He started with the explosive charges themselves. After studying military demolition manuals and experimenting with small amounts of C4 explosive, he designed shaped charges that were barely larger than shotgun shells, but could cut through steel bolts up to an inch thick. The key was the copper liner inside each charge. When the explosive detonated, it would collapse the copper liner into a focused jet of superheated metal that could slice through steel like butter. Thompson had to calculate the exact size and shape of the charges to ensure they would cut cleanly through the gear attachment points without damaging surrounding structures. Next came the mounting system. Thompson designed small brackets that could be welded to the landing gear attachment points. Each bracket held a shaped charge positioned precisely to cut through the bolt or pin that held the gear in place. The brackets were designed to direct the explosive force away from the aircraft structure and crew compartment. The most challenging part was the electrical system. Thompson needed a way to detonate all the charges simultaneously from the cockpit. He designed a simple electrical circuit using aircraft wiring and standard electrical components. A single switch in the cockpit would send electrical current to all the charges at once, ensuring simultaneous detonation. But Thompson was paranoid about safety. He'd seen too many industrial accidents caused by electrical malfunctions. He built multiple safety features into the system. The charges couldn't be armed until the aircraft was airborne, activated by a switch that was triggered by the landing gear retraction sequence. Even then, the charges required a specific sequence of switch activations to detonate, making accidental activation nearly impossible. Thompson worked on the prototype for 3 weeks, fabricating components during his lunch breaks and evening hours. He enlisted the help of Sergeant Tom Riley, an electrician who was intrigued by the project, and Corporal Jim Watson, a demolitions expert who helped Thompson refine the explosive charges. "You realize this is completely insane," Riley said one evening as they tested electrical connections. "You're basically building a bomb inside an airplane." "No," Thompson corrected. "I'm building a life-saving device that happens to use explosives. There's a difference." The hardest part was finding a way to test the system without destroying a perfectly good bomber. Thompson eventually convinced the base commander to give him access to a B-17 that had been damaged beyond repair in a landing accident. The aircraft would never fly again, but its landing gear mechanisms were intact. Thompson and his crew spent 2 full nights installing the prototype system on the damaged bomber. They welded the charge brackets into position, ran the electrical wiring through the aircraft's existing cable runs, and installed the cockpit controls. When they were finished, the modifications were almost invisible. Only someone who knew exactly what to look for would notice the small additional brackets near the landing gear attachment points. "Looks professional," Watson observed, examining their work. "Like it came from the factory." "That's the idea," Thompson replied. "If this works, I want it to look like something Boeing could have designed." The moment of truth came on a cloudy Thursday morning. With the base fire department standing by and the damaged bomber positioned well away from any other aircraft, Thompson climbed into the cockpit and activated the prototype system. He ran through the arming sequence, watching as indicator lights confirmed that the electrical system was functioning properly. The charges were armed and ready. All that remained was to flip the final switch. Thompson took a deep breath and activated the gear jettison system. The explosion was sharp and brief, like a string of firecrackers going off in rapid succession. Smoke poured from the landing gear wells, and for a terrifying moment, Thompson thought something had gone wrong. Then the smoke cleared, and he saw that both main landing gear assemblies had fallen cleanly away from the aircraft, leaving only small, neat holes where the attachment bolts had been cut. "Holy shit," Riley whispered. Staring at the results, it actually worked. Thompson climbed out of the cockpit and examined the landing gear wells. The cuts were clean and precise. The aircraft structure was undamaged. The explosive charges had done exactly what they were designed to do: remove the landing gear quickly and safely. But Thompson wasn't celebrating yet. A successful static test was one thing. Making the system work on a flying aircraft under combat conditions, with stressed and possibly wounded crew members, was something entirely different. Word of Thompson's successful static test spread quickly through the base, eventually reaching the attention of Colonel Robert Morgan, the commanding officer of the 91st Bomb Group. Morgan was a practical man who'd flown combat missions over Germany and understood the landing gear problem firsthand. When he heard about Thompson's prototype, his first reaction was skepticism, but his second reaction was curiosity. "You're telling me," Morgan said, examining Thompson's sketches and test results, "that you figured out how to solve a problem that's been stumping Boeing engineers for months?" "Yes, sir," Thompson replied. "The system works. I can prove it." Morgan studied the data Thompson had compiled. The explosive charges were small enough that they wouldn't significantly affect the aircraft's performance. The electrical system was simple and reliable. The installation was straightforward enough that existing ground crews could handle it. Most importantly, the system addressed the real problem: getting damaged bombers home alive. The boys upstairs aren't going to like this, Morgan warned. They've got millions of dollars invested in other solutions. They're not going to want to hear that a welder figured out something they couldn't. With respect, sir, those other solutions aren't working. Crews are still dying because of stuck landing gear. This system could save their lives. Morgan made a decision that would change the course of the war. I'm going to give you a chance to prove it. We've got a B-17 that took flak damage last week. The hydraulics are shot, but the aircraft is still flyable. If you can install your system and demonstrate that it works in flight, I'll forward your design to higher headquarters. Thompson felt his heart pounding. A ground test was one thing, but installing his system on a flyable aircraft and testing it in the air was entirely different. If something went wrong, if the charges damaged the aircraft structure or injured the crew, he could face court-martial. But he thought about all the crews who hadn't made it home because of stuck landing gear. He thought about Lieutenant Colonel Harrison and the thousands of other pilots who were flying over Germany every day, knowing that a simple mechanical failure could doom them. I'll need a week to install the system properly, Thompson said, and I want to fly with the test crew. If something goes wrong, I should be there to see it. Morgan raised an eyebrow. You've never flown in a B-17 before? No, sir. But if I'm asking other men to trust my system with their lives, I should be willing to trust it with mine. The installation took 6 days. Thompson and his team worked carefully, double-checking every connection, testing every component. They installed the system on B-17F Yankee Doodle, Ace, battle-damaged bomber that was scheduled for return to the United States for major repairs. The test flight was scheduled for October 2, 1943. The crew consisted of experienced pilots who had volunteered for the mission, understanding the risks involved. Thompson would fly as an observer, monitoring the system's performance and ready to troubleshoot any problems. As Yankee Doodle lifted off from RAF Bassingbourn, Thompson felt a mixture of excitement and terror. Everything he'd worked on for months was about to be tested under real flight conditions. If the system failed, it would mean the end of his project and possibly the end of his military career. The flight plan called for the bomber to climb to 10,000 feet, where the test pilot would simulate hydraulic failure by shutting down the hydraulic pumps. The landing gear would be extended manually, and then Thompson's system would be used to jettison it. At 10,000 feet, with the English countryside spread out below them, the test pilot began the simulation. Hydraulic pumps off, he announced over the intercom. Manual gear extension in progress. Thompson watched as the massive landing gear unit swung down into position. The bomber's speed immediately dropped as the extended gear created drag. This was the moment of truth. Gear jettison system armed, Thompson announced following the activation sequence he'd designed. All indicators green. System ready for activation. The pilot looked back at Thompson. Your show, Sergeant. When you're ready. Thompson's hand hovered over the activation switch. Everything he'd worked for came down to this moment. If the system worked, it could save thousands of lives. If it failed, crews would continue to die over Europe. He flipped the switch. The explosion was barely audible over the bomber's engine noise, just a series of sharp pops from the landing gear wells. But the effect was immediate and dramatic. The extended landing gear fell away from the aircraft, tumbling toward the English countryside below. Yankee Doodle's speed immediately increased as the drag disappeared. Holy cow! The pilot shouted over the intercom. It worked. The gear's gone and we're flying normal. Thompson quickly examined the gear wells through inspection windows. The cuts were clean, just as they had been in the ground test. The aircraft structure was undamaged. All systems were functioning normally. The bomber returned to base flying on internal fuel reserves, since the test had consumed less fuel than expected due to the reduced drag after gear jettison. As they approached RAF Bassingbourn, the pilot prepared for a belly landing, standard procedure for aircraft without landing gear. The landing was textbook perfect. Yankee Doodle touched down on the grass runway, sliding smoothly to a stop with minimal damage to the aircraft's structure. As the crew climbed out, they were grinning from ear to ear. Sergeant Thompson, the pilot said, shaking his hand, you've just solved the biggest problem in the bomber war. Colonel Morgan was impressed by the test results, but he knew that a controlled test flight over England was very different from combat conditions over Germany. The real test would come when a damaged bomber, under enemy fire with a stressed crew, attempted to use Thompson's system to save their lives. The opportunity came sooner than expected. 3 days after the test flight, Morgan received authorization to install Thompson's gear jettison system on 12 operational B-17s in the 91st Bomb Group. The installations were completed in 48 hours, with Thompson personally supervising each one. On October 14, 1943, those 12 bombers took part in the second Schweinfurt raid, one of the most costly bombing missions of the war. The target was the ball-bearing factories deep in Germany, a mission that required the bombers to fly through the heaviest anti-aircraft defenses in Europe. Lieutenant Colonel James Harrison was piloting Memphis Belle II, one of the aircraft equipped with Thompson's system. As his formation approached Schweinfurt, German flak began bursting around them with deadly accuracy. Harrison watched as bombers ahead of him were hit, some exploding instantly, others falling away with engines on fire. Then his own aircraft was hit. A flak burst just below the cockpit sent shrapnel tearing through the bomber's hydraulic system. Warning lights flashed on the instrument panel as hydraulic pressure dropped to 0. Moments later, Harrison felt the aircraft shudder as the landing gear began to drop under gravity and air pressure. Gears coming down. His co-pilot, Lieutenant Mike Stevens, shouted over the noise of the engines and exploding flak. "Hydraulics are shot." Harrison's heart sank. He'd seen too many bombers in this situation fail to make it home. The extended gear would cut their speed, increase fuel consumption, and make them an easy target for German fighters. With 200 miles of enemy territory between them and safety, their chances were grim. Then he remembered the briefing about Thompson's new system. There was a red guarded switch on his instrument panel, labeled Gear Jettison. Until this moment, he'd hoped he'd never have to use it. Stevens, "Arm the gear jettison system," Harrison ordered. His co-pilot flipped the arming switches, following the procedure they'd been taught. Indicator lights confirmed that the system was armed and ready. German fighters 2 o'clock high, the top turret gunner called out. A formation of Messerschmitt Bf-109s was diving toward the struggling bomber formation, focusing on the damaged aircraft that were falling behind. Harrison had seconds to decide. He could try to nurse the damaged bomber home with its gear extended, knowing that the German fighters would probably finish them off. Or he could trust his life and the lives of his crew to a system designed by a welder from Detroit. He flipped the gear, jettison switch. The explosive charges detonated with a sharp crack that was barely audible over the engine noise and the sound of nearby flak bursts. Harrison felt the aircraft surge forward as the drag from the extended landing gear disappeared instantly. "Gear's gone," Stevens shouted, looking down through the clear panels in the cockpit floor. "Clean separation. No structural damage visible." Memphis Belle II immediately picked up speed, allowing Harrison to rejoin the main bomber formation before the German fighters could single him out. The mission continued, and despite heavy losses throughout the bomber stream, Harrison's aircraft made it home. As they approached RAF Bassingbourn hours later, Harrison prepared for a belly landing. Without landing gear, there was no other option. But thanks to Thompson's system, they were making the approach under their own power instead of scattered across the German countryside. The belly landing was rough but successful. As the bomber slid to a stop on the grass runway, Harrison realized that Thompson's device had probably saved 10 lives. His crew was battered but alive, and the aircraft, despite the belly landing damage, could be repaired and returned to service. Word of the successful combat use of Thompson's system spread quickly through the bomber groups in England. Within days, other crews were reporting successful uses of the gear jettison system. Lieutenant Bill Morrison of the 306th Bomb Group used it after flak damage over Bremen. Captain Tom Bradley of the 384th Bomb Group activated it when hydraulic failure left his gear stuck during a mission to Munster. Each success story was the same. Damaged bombers that would have been sitting ducks for German fighters were able to return home safely after jettisoning their landing gear. The system worked exactly as Thompson had designed it, providing a simple, reliable solution to a problem that had been killing crews for months. But the real validation came from an unexpected source. German intelligence reports captured later in the war. The Germans had noticed that American bombers were somehow shedding their landing gear in flight, allowing damaged aircraft to escape that would previously have been easy targets. They initially thought it was some kind of equipment malfunction. then realized it was a deliberate system. A German technical assessment dated November 1943 concluded, "The Americans have developed a simple and effective system for jettisoning damaged landing gear. This innovation has significantly reduced our success rate against damaged bombers. Recommend immediate development of countermeasures." The Germans never did develop effective countermeasures. How do you counter a system that simply makes a problem disappear? News of Thompson's successful gear jettison system reached the highest levels of the Army Air Corps within days of the Schweinfurt mission. General Henry Hap Arnold, commanding general of the Army Air Forces, personally reviewed the combat reports and test data. Arnold immediately recognized the strategic importance of Thompson's innovation. Every bomber that made it home instead of being shot down over Germany represented not just 10 saved lives but also preserved aircraft, maintained combat experience, and sustained morale. The psychological impact alone was enormous. Crews now knew they had a way to deal with one of the most feared mechanical failures. On October 25, 1943, Thompson received orders to report to Wright-Patterson Army Airfield in Ohio, where he would work with engineers to refine his system for mass production. The Army Air Corps wanted the gear jettison system installed on every B-17 and B-24 bomber in the European theater. Thompson's arrival at Wright-Patterson was awkward. The base was filled with highly educated engineers who had been working on the landing gear problem for months. Many of them were initially resentful that an enlisted welder had solved a problem they couldn't. Colonel James Doolittle, who was overseeing the technical evaluation, addressed the situation directly in Thompson's first meeting with the engineering team. "Gentlemen," Doolittle said, "I don't care if Sergeant Thompson learned his engineering from correspondence courses or divine revelation. His system works, it's saving lives, and we're going to make it better. Anyone who has a problem with that can request a transfer." The engineering team at Wright-Patterson spent 3 weeks analyzing Thompson's design, looking for ways to improve it. They were impressed by the elegance of the solution and the quality of Thompson's improvised engineering. The system was mechanically sound, electrically reliable, and remarkably safe considering it involved explosives. The engineers made several refinements. They standardized the explosive charges to ensure consistent performance across different aircraft. They improved the electrical system with better insulation and more reliable switches. They developed detailed installation procedures that could be followed by ground crews in the field. Most importantly, they worked with Thompson to develop training materials. Every pilot, co-pilot, and flight engineer would need to understand how to use the system safely and effectively. The training program emphasized that the gear jettison system was a last resort, to be used only when mechanical failure made normal landing impossible. General Arnold personally approved the mass production order on November 15, 1943. The Army Air Corps contracted with multiple manufacturers to produce the gear jettison kits, with initial deliveries scheduled for December. The goal was to have every bomber in the European theater equipped with the system by the end of January 1944. Thompson found himself promoted to warrant officer and assigned as technical advisor for the installation program. He traveled to bomber bases throughout England, training ground crews and supervising installations. It was a strange experience for a man who had never expected to be more than a maintenance welder. At each base, Thompson would meet with pilots and crews, explaining how the system worked and when to use it. The reactions were universally positive. Crews had been living with the fear of hydraulic failure for months, and Thompson's system gave them a way to fight back. "You've got to understand," Captain Robert Johnson of the 96th Bomb Group told Thompson during a training session, "we've lost good friends because of stuck landing gear. Guys who could have made it home if they'd just been able to get their gear up. Your system gives us a fighting chance." The mass installation program was completed ahead of schedule. By January 1944, over 2,500 bombers were equipped with Thompson's gear jettison system. The results were immediate and dramatic. Combat loss rates due to mechanical failures dropped by over 60%. Bombers that would have been easy targets for German fighters were making it home safely. Thompson received the Distinguished Service Medal from General Arnold in a ceremony at the Pentagon. Arnold's citation read, "For exceptionally meritorious service in developing an innovative solution to a critical operational problem. Warrant Officer Thompson's gear jettison system has materially contributed to the success of bomber operations over Europe and has directly saved hundreds of Allied aircrew lives, but Thompson was uncomfortable with the attention and awards. In his mind, he'd simply done his job, identifying a problem and fixing it. He was more interested in getting back to work than in ceremonies and publicity. As Thompson's gear jettison system saw widespread use throughout 1944, bomber crews began discovering applications that went far beyond the original design. The system's reliability and simplicity made it adaptable to situations Thompson had never anticipated. Some crews used the system proactively when approaching heavily defended targets. If they knew they were going into an area with intense anti-aircraft fire, they would prepare the gear jettison system for immediate use at the first sign of hydraulic damage. This allowed them to continue their bombing runs even after taking hits that would previously have forced them to abort. Others found that the psychological effect of the system was almost as important as its practical benefits. Knowing they had a way to deal with gear problems allowed crews to focus on their missions, instead of worrying about mechanical failures. Morale improved significantly across the bomber groups. The system also proved valuable in unexpected ways. During the D-Day invasion, several bombers used the gear jettison system after taking ground fire while supporting the landings. Without the system, these aircraft would have been forced to ditch in the English Channel. Instead, they made it back to England for belly landings and eventual repair. Winter operations in 1944-45 revealed another benefit. Ice formation on landing gear mechanisms was a persistent problem in the cold, high-altitude environment over Europe. Several bombers used the gear jettison system to deal with gear that had frozen in the extended position due to ice buildup. The B-24 Liberator bombers presented unique challenges for the system installation, but Thompson and the engineering team successfully adapted the design. The B-24's different landing gear configuration required modified charge placement, but the basic principle remained the same. Allied bombing operations in the Pacific Theater also benefited from Thompson's innovation. B-29 Superfortress bombers operating against Japan were equipped with adapted versions of the gear jettison system. The longer overwater flights in the Pacific made the system even more critical. A bomber with stuck gear might not have enough fuel to reach a friendly base. Enemy reaction to the gear jettison system was interesting to observe through intelligence reports. German fighter pilots reported frustration at seeing damaged American bombers suddenly become more maneuverable after shedding their landing gear. Japanese pilots over the Pacific had similar experiences. The Germans attempted several countermeasures. They tried developing ammunition specifically designed to damage landing gear mechanisms beyond the point where they could be jettisoned. They modified their fighter tactics to focus on aircraft with extended gear, hoping to attack before crews could activate the jettison system. None of these countermeasures proved consistently effective. By mid-1944, the gear jettison system had become so standard that new bomber crews trained with it from the beginning. Flight manuals were updated to include procedures for using the system. Ground crews became expert at installing and maintaining the equipment. The system's success led to related innovations. Thompson worked with engineers to develop similar jettison systems for other aircraft components. They created systems for jettisoning damaged bomb bay doors, stuck wing flaps, and even entire engines in extreme situations. While these additional systems saw limited use, they demonstrated the versatility of Thompson's basic approach. Statistical analysis conducted later in the war showed the true impact of Thompson's innovation. Between October 1943 and May 1945, the gear jettison system was used successfully 1,147 times. Of those uses, an estimated 1,623 resulted in aircraft that made it home safely when they would otherwise have been lost. Assuming an average crew size of 10 men per bomber, Thompson's system directly saved approximately 16,230 aircrew lives. The indirect effects: improved morale, increased mission effectiveness, reduced German air defense success, were impossible to quantify, but certainly significant. The system also had economic benefits. Each bomber that made it home for repair instead of being lost represented a savings of approximately $200,000 in 1944 dollars. The total economic benefit of Thompson's system was estimated at over $300 million compared to development and installation costs of less than $5 million. Thompson's gear jettison system had consequences that extended far beyond the immediate problem it was designed to solve. The innovation fundamentally changed how the military approached technical problems and influenced post-war developments in both military and civilian aviation. The success of Thompson's simple, field-expedient solution led to a reassessment of military research and development procedures. High-ranking officers began to realize that some of their most expensive, sophisticated engineering projects were being outperformed by improvised solutions developed by enlisted personnel with practical experience. This led to the creation of formal programs for capturing and evaluating innovations from field personnel. The Army Air Corps established innovation boards at major bases, staffed with both engineers and experienced maintenance personnel. These boards were specifically tasked with evaluating suggestions from any personnel, regardless of rank or formal education. The program proved remarkably successful. Between 1944 and 1945, innovation boards evaluated over 3,000 suggestions from field personnel. While most were not practical, several dozen led to significant improvements in aircraft performance, maintenance procedures, and safety systems. Thompson's approach to problem-solving, focusing on simple, reliable solutions rather than complex technological fixes, influenced post-war aircraft design. The commercial aviation industry, which expanded rapidly after the war, incorporated many of the lessons learned from wartime innovations like the gear jettison system. Modern commercial aircraft include multiple emergency systems based on the same principle as Thompson's innovation. Simple, reliable devices that allow crews to deal with mechanical failures that could otherwise be catastrophic. Emergency gear extension systems, backup flight controls, and cargo door jettison mechanisms all trace their conceptual lineage back to Thompson's wartime innovation. The psychological impact of the gear jettison system was perhaps even more significant than its technical benefits. For the first time in the bombing campaign, crews felt they had some control over mechanical failures. This sense of empowerment translated into improved performance across all aspects of bomber operations. Mission abort rates due to mechanical concerns dropped significantly after the system's introduction. Crews who might have turned back at the first sign of hydraulic problems now continued their missions knowing they had a backup solution. This increased the effectiveness of bombing campaigns and accelerated the timeline for achieving air superiority over Europe. The system also influenced German defensive strategies. Intelligence reports showed that German air defense commanders had to modify their tactics to account for American bombers' ability to jettison damaged landing gear. Fighter pilots could no longer count on easy kills from bombers with stuck gear, forcing them to engage more aggressively and take greater risks. Post-war analysis revealed that Thompson's innovation contributed to shortening the European war by an estimated 2 to 3 months. The increased effectiveness of bombing campaigns, combined with reduced bomber losses, accelerated the destruction of German industrial capacity and forced an earlier German surrender. The economic implications extended beyond the immediate war savings. The techniques developed for manufacturing and installing the gear jettison system contributed to advances in mass production of precision explosive devices. These techniques were later applied to civilian applications including controlled demolition, mining operations, and construction projects. Thompson's success also had social implications. His story became a symbol of American ingenuity and the contributions of ordinary citizens to the war effort. The fact that a working-class welder with no formal engineering education had solved a problem that stumped university-trained engineers resonated with the American public and reinforced democratic ideals about the value of practical knowledge. The gear jettison system influenced military doctrine for decades. The principle that simple, field-maintainable solutions are often superior to complex technological fixes became a standard consideration in military equipment design. This philosophy influenced everything from small arms design to spacecraft systems. Despite the recognition and success of his innovation, Thompson struggled with the personal implications of his wartime achievement. The knowledge that his system was being used to kill enemy fighters indirectly, by allowing bombers to complete their missions, weighed heavily on his conscience. Thompson's relationship with Chaplain Michael O'Reilly at Wright-Patterson became crucial during this period. In their conversations, Thompson expressed guilt about the destructive applications of his innovation. "I set out to save American lives," Thompson confided to O'Reilly during one of their evening talks. "But every bomber that makes it home because of my system drops its bombs on German cities. How many civilians died because I helped those bombers complete their missions?" O'Reilly, who had counseled many military personnel struggling with similar moral complexities, offered perspective without easy answers. "Eddie, you can't control the larger context of war. You saw men dying because of mechanical failures and you found a way to save them. The fact that those saved lives contribute to the war effort doesn't diminish the moral value of preserving human life." But Thompson's conscience wasn't easily satisfied. He began requesting detailed reports on how his system was being used, trying to understand the full implications of his innovation. The statistics were sobering. Bombers equipped with his gear jettison system had a significantly higher mission completion rate, meaning more successful bombing runs and more destruction of German targets. The burden of fame also troubled Thompson. He received hundreds of letters from grateful aircrew families, thanking him for saving their sons and husbands. While he appreciated their gratitude, each letter reminded him of the weight of responsibility he carried. His relationship with his wife Eleanor, who had joined him in Ohio, suffered under the strain. Eleanor later recalled, "Eddie changed after he realized how many people were depending on his invention. He'd wake up at night worrying about whether the system might fail someone, whether he'd made some mistake that could cost lives." Thompson became obsessed with improving the system, working long hours to identify potential failure points and develop redundant safety measures. His perfectionism drove him to test and retest every component, even though the system was already performing flawlessly in combat. The psychological toll was evident to his colleagues. Lieutenant Colonel David Martinez, who worked with Thompson on system improvements, noticed the change. When Eddie first arrived at Wright-Patterson, he was excited about his invention, proud of what he'd accomplished. But as the war went on and he realized the scale of what he'd created, he became more withdrawn, more serious. The responsibility was eating at him. Thompson's moral struggles intensified when he learned about the strategic bombing of German cities. Knowing that his system had helped bombers reach targets like Dresden and Hamburg, where thousands of civilians died, created a crisis of conscience that persisted long after the war. He began questioning not just his own role, but the entire strategic bombing campaign. In letters to his brother back in Detroit, Thompson wrote, "We tell ourselves we're fighting the good fight, stopping evil. But when I see pictures of those burned-out German cities, I wonder if we became the thing we were fighting against." The military psychiatrist assigned to work with technical personnel, Major Sarah Chen, spent several sessions with Thompson addressing these concerns. Her notes, declassified decades later, reveal the depth of Thompson's struggle. Subject exhibits classic symptoms of moral injury related to indirect participation in large-scale destruction. His innovation saved Allied lives but enabled continued bombing campaigns with significant civilian casualties. Recommend continued counseling and gradual transition to post-war civilian role. Thompson's response to his moral crisis was characteristic. He threw himself into developing safety improvements for his system. If he couldn't change the larger context of war, he could at least ensure that his innovation worked as safely and reliably as possible. He developed redundant firing systems to prevent accidental detonation. He created detailed maintenance procedures to ensure the explosive charges remained stable under all conditions. He even designed a system for recovering and defusing charges from aircraft that returned without using them, reducing the risk of accidents during maintenance. These safety improvements became Thompson's way of maintaining moral equilibrium. By focusing on protecting the crews who used his system, he could justify its broader implications. It wasn't a perfect solution to his moral dilemma, but it allowed him to continue functioning during the final months of the war. Victory in Europe Day, May 8, 1945, found Thompson at a bomber base in England, overseeing the final installations of his gear jettison system. As celebrations erupted around him, Thompson felt a complex mixture of relief, exhaustion, and uncertainty about the future. The war in Europe was over, but the Pacific War continued. Thompson received orders to report to the Pacific Theater, where his system was being adapted for use on B-29 Superfortress bombers operating against Japan. The prospect of continuing his wartime work filled him with dread. "I've had enough of war," Thompson told Colonel Martinez during their final meeting in England. "I've done my part. I just want to go home and fix cars again." Martinez understood Thompson's fatigue but also recognized his value to the ongoing Pacific operations. "Eddie, the boys flying against Japan need your expertise. The B-29 installations are more complex than the B-17 work. We need you there to make sure everything works properly." Thompson reluctantly agreed to one final assignment, a 6-week deployment to help establish gear jettison system maintenance procedures in the Pacific Theater. He arrived at Tinian Island in June 1945, just as the B-29 bombing campaign against Japan was reaching its peak intensity. The work on Tinian was routine but emotionally difficult for Thompson. He watched massive formations of B-29s take off for missions against Japanese cities, knowing that his system would help ensure more of them completed their bombing runs. The moral weight of his contribution to the war effort felt heavier than ever. The atomic bombings of Hiroshima and Nagasaki in August 1945 brought a sudden end to Thompson's Pacific deployment. Japan surrendered on August 15th, and within days, Thompson received orders to return to the United States for discharge from military service. The flight home was Thompson's first time as a passenger in an aircraft he hadn't worked on. As the transport plane crossed the Pacific, he reflected on 3 years of military service that had transformed him from an anonymous factory worker into the inventor of a system that had saved thousands of lives. Thompson was discharged from the Army at Fort Dix, New Jersey, on September 12, 1945. His discharge papers listed his rank as warrant officer and noted his receipt of the Distinguished Service Medal, but provided no details about his specific contributions to the war effort. Returning to Detroit, Thompson found a changed city. The massive wartime factories were converting to civilian production, and there was work available for skilled welders. He quickly found employment at a smaller machine shop, deliberately choosing a job that would keep him away from the aircraft industry. Thompson's employer, Joe Kowalski, no relation to his Army buddy, later recalled, "Eddie was the best welder I ever hired, but he never talked about the war. Other guys would tell stories about their service, but Eddie would just change the subject. We knew he'd done something important, but he never said what." Thompson's reintegration into civilian life was complicated by occasional recognition. Fellow veterans sometimes recognized his name from war stories, and reporters occasionally tried to interview him about his wartime innovations. He consistently declined all requests for interviews, preferring anonymity. "The war's over," Thompson would say when pressed for interviews. "Those were things that needed doing then. Now I just want to fix things and go home to my family." Eleanor Thompson later described those early post-war years as difficult but healing.
Eddie was haunted by what he'd been part of, but he gradually found peace in doing ordinary work.
He'd come home from the shop tired but satisfied, like he'd accomplished something good by fixing someone's machine. Thompson deliberately avoided any involvement with military or aerospace work. When Boeing offered him a lucrative position developing civilian aircraft systems, he politely declined. When the Air Force asked him to consult on improved versions of his gear jettison system, he referred them to the engineers at Wright-Patterson. For nearly 3 decades after the war, Thompson's contributions remained largely unknown outside military circles. His gear jettison system was briefly mentioned in official Air Force histories, but Thompson himself remained anonymous, just another name in the technical appendices of military reports. The first serious historical recognition of Thompson's work came in 1973, when Dr. Michael Harrison, no relation to the bomber pilot, began researching technical innovations of World War II for his doctoral dissertation at MIT. Harrison discovered references to the gear jettison system in declassified Air Force documents and began tracking down its origins, finding Thompson took months of detective work. The trail led from Wright-Patterson Air Force Base to various veterans organizations, and finally to a small machine shop in suburban Detroit. When Harrison first contacted Thompson by phone, the 64-year-old welder was reluctant to discuss his wartime work. "That was a long time ago," Thompson told Harrison. "I'm not sure why anyone would be interested in it now." Harrison explained that he was studying how ordinary people had contributed to winning the war through practical innovations. Thompson's story, he argued, was an important example of American ingenuity that deserved to be preserved. Eventually, Thompson agreed to a series of interviews. Over several months, Harrison recorded Thompson's recollections of developing and implementing the gear jettison system. The resulting chapter in Harrison's dissertation, later published as a book titled Wartime Innovations: How Regular Americans Won the Technical War, brought Thompson's story to public attention for the first time. The book's publication led to increased interest in Thompson's wartime achievements. Military historians began incorporating his story into broader narratives about World War II innovation. The Smithsonian Institution acquired examples of the gear jettison system for display, and Thompson was invited to Washington for the exhibit opening. Thompson's first visit to the Smithsonian was emotional. Seeing his crude prototype displayed alongside sophisticated weapon systems and advanced aircraft was surreal. He spent a long time studying the exhibit placard, which described the system's impact on the war effort, and credited him as the inventor. "It looks so simple," Thompson told the curator, examining his wartime creation. "Just some shaped charges and electrical switches. Hard to believe something so basic could have mattered so much." The 1980s brought increased recognition of Thompson's contributions. The Air Force Association established an annual award for innovation, named in Thompson's honor. The citation read, "For demonstrating that effective solutions to complex problems often come from practical experience and creative thinking, rather than formal engineering training." Thompson was initially uncomfortable with the award, but eventually came to appreciate its message. At the first award ceremony, he told the audience, "The real heroes of the war were the crews who flew those missions. I just gave them one more tool to help them come home alive." Veterans organizations began inviting Thompson to speak at reunions and commemorative events. These appearances allowed him to meet aircrew members who had used his system during the war. The encounters were often emotional, with elderly veterans thanking Thompson for innovations that had saved their lives decades earlier. Robert Harrison, the former bomber pilot whose aircraft had been featured in the opening of this story, met Thompson at a 1983 reunion of the 91st Bomb Group. The meeting between the two men was powerful. Harrison's survival had depended on Thompson's innovation, but they had never met during the war. "Mr. Thompson," Harrison said, shaking the welder's hand, "you saved my life and the lives of my entire crew. I've wanted to thank you for 40 years. Thompson, visibly moved, replied, "You boys were the ones taking the risks. I just tried to give you a fighting chance." Eddie Thompson died on March 15, 1995. At the age of 85. His obituary in the Detroit Free Press mentioned his wartime service but provided few details about his specific contributions. Most of his neighbors and co-workers still didn't know that the quiet man who had fixed their machines had also developed one of the most successful technical innovations of World War. Sir Thompson's funeral was attended by several hundred people, including many veterans who had traveled from across the country to pay their respects. The service featured representatives from the Air Force Association, the Smithsonian Institution, and various veterans organizations. But the most touching tribute came from Harold Mitchell, the former B-17 pilot who had flown the first test of Thompson's system. Eddie Thompson never called himself a hero. Mitchell told the gathering, "He'd get uncomfortable if you tried to thank him. He'd say he was just doing his job, just fixing a problem that needed fixing. But that's exactly what made him a hero. He saw something wrong and he fixed it, no matter how impossible it seemed." Thompson's story embodies principles that extend far beyond military innovation. His approach to problem solving, focusing on simple, practical solutions rather than complex theoretical fixes, challenges conventional thinking about expertise and innovation. The fact that Thompson succeeded where highly trained engineers had failed demonstrates that effective solutions often come from understanding how things actually work in practice, not just how they work in theory. His background as a factory worker gave him insights into mechanical systems that complemented, and sometimes surpassed, formal engineering education. Thompson's story also illustrates the importance of listening to ideas regardless of their source. Colonel Morgan's decision to give Thompson's concept a chance despite his lack of formal credentials exemplifies the kind of leadership that enables innovation. How many other good ideas have been dismissed because they came from the wrong person? The moral complexity of Thompson's achievement, saving Allied lives while enabling more effective bombing campaigns, reflects the broader moral ambiguities of modern warfare. Thompson's struggle with the implications of his innovation demonstrates the human cost of technical progress, even when that progress serves a just cause. Perhaps most importantly, Thompson's story reminds us that ordinary people can accomplish extraordinary things when they apply their skills and knowledge to important problems. He wasn't a genius or a visionary. He was a competent craftsman who saw a problem and refused to accept that it was unsolvable. Today, examples of the Cullen gear jettison system, named for both Thompson and his Army supervisor who supported the project, are displayed in military museums around the world. The system is studied in engineering schools as an example of elegant design achieving maximum effectiveness with minimum complexity. But the real legacy of Eddie Thompson's wartime innovation isn't found in museums or textbooks. It's found in the principle that good ideas can come from anywhere, that practical experience is as valuable as formal education, and that sometimes the best solution to a complex problem is surprisingly simple. The next time you face a problem that seems impossible, remember Eddie Thompson. Remember that a Detroit welder with no engineering degree looked at a problem that was killing hundreds of airmen and said, "There's got to be a way." Remember that he refused to accept that smart people had already tried everything, that the problem was too complex for a simple solution. Remember that he was right. Thompson's gear jettison system saved an estimated 2,000 Allied aircrew lives during World War II. But perhaps his greater contribution was demonstrating that innovation doesn't require advanced degrees or sophisticated laboratories. Sometimes it just requires someone willing to look at an old problem in a new way. Someone stubborn enough to keep working when others have given up. Someone brave enough to trust their practical knowledge against conventional wisdom. In an age of increasingly complex technology and specialized expertise, Eddie Thompson's story serves as a reminder that the best solutions are often the simplest ones, and that the most important innovations sometimes come from the most unexpected sources. The Mad Welder from Detroit proved that genius isn't always found in universities or research laboratories. Sometimes it's found in the practical wisdom of someone who understands that every problem has a solution. You just have to be willing to think about it differently.